What is the thermal energy for n moles of monatomic gas where each molecule has 3 degrees of freedom representing the 3 dimensions of translational motion? Let me start with that question. What we've seen is that the equipartition theorem essentially says that for a mole of, I'm just going to say maybe things, you could say particles, maybe you could say molecules, there's going to be an amount of thermal energy of 1/2 RT for each degree of freedom that each of those particles has. And so there's different ways of saying that. We saw earlier that the energy per mole for a monatomic gas was 3/2 RT, and that's basically an expression of what I just said. But now we're being asked for the total amount of thermal energy for n moles. So if I have 3/2 RT per mole, and then I multiply by the number of moles, I'd have the total energy. So that gives me 3/2 nRT. And you might note I'm not writing this on the whiteboard this time because hopefully you can follow what I'm saying verbally. We've talked about this in some other examples, so hopefully it's making sense. The second question says, what is the thermal energy for n moles of diatomic gas where each molecule has 5 degrees of freedom representing translation plus 2 rotational types of motion? So that's what we've been exploring here in the last example. But in both cases, we're just simply looking at how to get to the kinds of expressions that we saw on the key concepts page, where it was, instead of just 3/2 RT, which was energy per mole, is 3/2 nRT, which is total thermal energy for a monatomic gas. And then the second one, 5/2 nRT, is the total thermal energy for n moles of a diatomic gas.